All right, this is going to be the Chapter 12 quiz tips video for our chemistry class. I just want to go through the practice quiz. I'm going to show you most of it, talk you through some strategies a little bit, give you, hopefully a little bit of help. And if you are struggling on these problems and not getting the answers that I'm showing you, then make sure that you reach out to your teacher because we can't help you if we don't know you're struggling. Okay, so first, what is the difference between a limiting and an excess reactant? So we're always talking about reactants with these two words, limiting reactant, excess reactant. Remember, limiting is limiting how much product we can make. And the reason why it limits how much product we can make is because it runs out. So limiting reactant is the one that gets used up. It runs out in the reaction. You can say it's the reactant that limits the amount of product you can make. That's absolutely true. Excess is the one that has leftovers. Excess has leftovers, okay? So I think these two, because they are opposite of each other and these are opposite of each other, those work better for definitions as far as memory goes. But if instead of this, you wanted to write it's the one that limits the amount of product in the reaction, that's great. But you still have to remember that excess is a reactant that does not get used up. It has reactant remaining after the completion of the reaction. Okay, percent yield. Our practice quiz says, what is percent yield used for? Well, let's just think about the formula for a second. Percent yield equals actual yield over theoretical yield times 100. We always multiply by 100 at the end to change something into a percent. Okay, so actual yield over theoretical yield. This is what your experiment or your reaction is actually yielding. So what is actually created. Theoretical is in a perfect world, how much would be created if everything went perfectly, okay? So actual over theoretical times 100. What would this actually be used for? Well, this is going to tell us how efficient our reaction is, or how perfect our reaction is another way to look at it, because if you have 100% yield, it's perfect. It's exactly what the theoretical yield is. But if you have a 50% yield, then it's far from perfect, right? So percent yield is telling us, how good our reaction system is, how well it's performing, efficiency of a reaction and whatnot. It's used a lot in businesses to see how well they're producing products from what they're expecting to be able to produce. Okay, now let's get into the problems. Number 3, wanted you first to balance this lovely chemical equation. So starting off, the only thing that's not balanced, well, iron, oxygen, neither of them are balanced, but we have an even versus an odd in our oxygen. So we want to fix that. 2 and 3 will get us 6 oxygens on both sides. Now I have a total of 4 irons here, so we'll balance that with a 4 there. And we're going to use this reaction for the next 2 parts of this problem. So the first one says, how many moles of oxygen are required to react with 27.6 moles of iron oxide? And remember, the steps for these problems are all on our molar map. So if you have moles of one thing, you're trying to find moles of another thing, then you can just use the one step, which is the mole ratio. Okay, so right here from, let's see, again, we're given moles of iron and we want to know how many moles of oxygen. So this is the mole ratio, 4:3, and that's the only thing we need for this problem. So we set our problem up starting with what we're given, 27.6 moles of iron. And we know that there are 4 moles of iron for every 3 moles of oxygen. The iron needs to cancel, so we'll put 4 moles of Fe on the bottom for every 3 moles of O2 on the top. And that's where we stop because it's asking for moles, okay? So moles of Fe, moles of Fe. 27.6 times 3, divide by 4. We are allowed 3 sig figs because of this value here. So we get 20.7 moles of oxygen. Part B, they give you grams of iron, and we want to know how many grams of iron oxide of rust are going to form, okay? So we're starting with 32.50 grams of iron. That was given to us in the problem, and we are trying to find grams of something else. So I'm going from mass of iron, mass of A, to mass of B. So 3 steps now. Molar mass gets us to moles. Mole ratio converts us to a new substance. And then molar mass again gets us to a new substance's mass. Okay, so for iron, our molar mass is our first step. 1 mole of Fe is 55.8 grams. The mole ratio in this problem is iron compared to iron oxide. We don't really care too much about the oxygen in this problem because it's not part of it. So 4 moles of iron for every 2 moles of rust. I'm putting iron on the bottom again because I'm trying to cancel iron. So 2 moles of Fe2O3 goes on the top. Our last step is molar mass to get 2 grams of Fe2O3. Actually, I misread the question. It's not asking for grams. It's asking for formula units. So if you wanted to look here, we're going from mass of A because we are starting in grams, but we're trying to find formula units, which is a particle. So we went from mass to moles. We used the mole ratio. Now we're going to use Avogadro's number to get up to particles of B. So 1 mole of Fe2O3 is 6.02 times 10 to the 23rd formula units. And that is the unit for the particles here because this is an ionic compound. That would be molecules if we were talking about a covalent compound. It would be atoms if we were talking about an element like a metal or a monatomic gas. This one also gets limited to 3 sig figs because of Avogadro's number and the molar mass of iron. So we end up with 1.75 times 10 to the 23rd formula units of iron oxide. 1.75 times 10 to the 23rd. All right, that's number 3. Here comes number 4. We're going to get into limiting reactants now. Okay. So we have the equation this time. It tells us we have 16.7 grams of nitrogen and 4.2 grams of hydrogen. It says which reactant is limiting and how many grams of NH3 can be made. Remember, these problems will always have 2 full stoichiometry calculations, starting with your given values and ending with whatever we're trying to find. And then we have to compare those answers in order to figure out this piece. Okay, so 16.7 grams of nitrogen. 1 mole of nitrogen is 28.0 grams because it's diatomic, so we have to double that molar mass on the periodic table. Molar mass on this one is 1 mole of nitrogen for every 2 moles of NH3. Nitrogen on the bottom in order to cancel. 2 moles NH3 on the top. And my last step is to get to mass of NH3. So 1 mole of NH3 is 17.0 grams of NH3. So punching this one in, 16.7 divided by 28 times 2 times 17, and we get 3 sig figs for this one. We get 20.3 grams. Hydrogen, 4.2 grams of hydrogen is our starting point. 1 mole of hydrogen weighs 2.0 grams because it's diatomic, so we have to double its mass from the periodic table. Molar mass for hydrogen is 3 moles of hydrogen for every 2 moles of NH3. And our last step will end up being the same as above because we're trying to get to mass, and the molar mass of NH3 is not going to change from one problem to the other. All right, so now we go 4.2 divided by 2 times 2 divided by 3 times 17. We get 2 sig figs for this one, and it ends up being 24 grams of NH3. So now we have to interpret. We can't make both of these amounts. We can't add these together. Don't do anything crazy like that. When we hit 20.3 grams, the nitrogen will run out. We can never get to 24 grams because there's no more nitrogen to react and form NH3. So N2 was our limiting reactant, and this is how much NH3 can be made. And that's all theoretical, right? We're calculating how much should be able to be produced in a perfect world. So this is our theoretical yield for the next question. Number 5 says only 18.5 grams of NH3 are produced. What is the percent yield? Well, are produced. That is an actual yield. It is telling us what was actually produced. So that's actual. That goes on the top. If this number is bigger than what your theoretical yield was up here, that's okay. Sometimes that happens, okay? If you've been in class, that happened in our lab. So don't worry about it, okay? That's our actual yield, R produced. Our theoretical yield, we will always get with stoichiometry. Sometimes it's given in the problem if it's a really simple percent yield problem, but most of the time we're going to find that one with stoichiometry. So 20.3, and then multiply by 100. Okay, so this yield is 91.1%, which is actually really good for an industry. Okay, so 91.1% yield there. Okay, question number 6. This one's actually easier. Don't let it throw you off. Okay, some people, when we get to something easy, they think they're doing something wrong. Okay, don't let it throw you off. Same thing as last problem, but we've got moles of I2O5, moles of CO. We want to know how many moles of I2 are formed and what the limiting reactant is. Okay, so 25.3 moles of I2O5. Moles to moles, guys. Just look at your mole map. Moles to moles. All we need is a mole ratio. So this one's much simpler because we just need one step for the stoichiometry. I2O5 is 1 mole. And iodine is only 1 mole. Okay, I'm going to put my answer for that one down here. So that's 25.3 because multiplying and dividing by 1 doesn't change your answer, but we just changed our units to iodine. Okay, the other one, 124 moles, carbon monoxide. Mole ratio is 5 moles to 1 mole. Oops. All right, so 124 divided by 5, we're limited to 3 sig figs. We're going to end up with 24.8 moles of iodine. So which one's limiting? The one that gives you less, right? So carbon monoxide is the limiting reactant because it only gave us 24.8 moles. Then it runs out and we can't make any more iodine, okay? So 24.8 moles is our theoretical yield. Then down to number 7, 19 moles are produced. That's actual yield right there. So 19.0 over our theoretical, excuse me, from the previous question, times 100. And that one gives us 76.6%, 76.6% yield. Okay. All right, number 8. This one says you have 13.7 liters of C2H2 reacting, and they want to know how many grams of water are produced. Again, use your molar map, okay? Also, this isn't a limiting reactant problem. This is a simple problem, just one stoichiometry calculation. We have liters of C2H2, volume at STP. We are looking for grams of water, mass at, or mass B, okay? So we're gonna go from volume of A at STP and up and over to mass of B, okay? 13.7 liters C2H2. Remember that first step from volume to moles is molar volume, and that's a constant. 22.4 liters of C2H2 is 1 mole C2H2. The next step is a mole ratio. In this problem, 2 moles of C2H2 for every 2 moles of water. Yes, you can reduce that to 1 to 1. All right, it's not going to affect our answer because it is a 1-to-1 ratio, but one of my tips has been when you have the ability to reduce, and we had this earlier with a 4-to-2 ratio, I believe, you can reduce it in your head before you use it. That's totally fine. But if you make a simple math error there, it costs you points. You're gonna miss it, and it's gonna make your answer wrong, and then you're only gonna get, partial credit because you've made that mistake. If you use it as written, then you avoid that potential simple math error in your brain. All right, last one. 1 mole of water. We are trying to find grams, so we put the molar mass on top, 18.0 grams of water. All right, that one equals 11.0 grams of water because of your 3 sig fig limitation. Sig figs always matter for us, okay? So make sure that you're paying attention to that. Number 9 and number 10. Number 9 was a grams to grams limiting reactant problem, and number 10 was a percent yield that went along with that problem, okay? It is the same type of problem as questions 4 and 5. Same number of steps, same starting and ending positions on our molar map, and then another percent yield problem, okay? If you are having problems with it, please come see us, but I'm going to tell you the answer right now. C2H2 ends up being your limiting reactant. 10.8 grams is the number of grams of water that can be made in that reaction because of that C2H2 limiting. And then number 10 ends up with an 86.5% yield. So those are the answers to 9 and 10. Again, reach out to your teacher before we take our quiz if you need help with this. The minute before we take the quiz probably isn't the best time. So if you need help, send her an email right now so that you are ready and you can make a plan to be successful. All right. Thanks for tuning in, and we will see you in class.